we'll finish up these slides today. Zooming on down. Yeah, we did fancy things. We learned about some different kinds of types. We learned about division, disgusting. I want to teach you about the ones and zeros that I've been saying all this time. I want to teach you guys binary today because that has to do with space as well. So we're going to learn how much stuff you can shove into an int, into a double, into a char even, all right? So I'm excited. Let's talk about the sizes of types. And so these words, you will maybe hear them for the first time today. That's okay. Or if you've heard them before, that's cool too. We're going to go deeper. All right, let me make sure I have the right size pens for everything. Perfect. So every int, we like our int variables in this class, right? Every int is 4 bytes long. All right, I will explain exactly what I mean by that later. If that makes no sense to you, that's fine. But this table, I will explain enough today. I promise that when I show it to you again, you will understand it. Okay. So an int is 4 bytes. That is also 32 bits because there's 8 bits to a byte. And the numbers that you can store into an int are within this range. All right, negative 2 to the 31st power to positive 2 to the 31st power minus 1. Those are the range of numbers you can put into an int. Can't get any bigger or any smaller. Weird. Characters, the char type, they take up just 1 byte. They're so small. And they can hold 256 separate things, but we give half of the space for negative numbers. So you can store negative 128 to positive 127 in characters in 1 byte of space. We also have floating point types like double. Doubles are 8 bytes, and they store their numbers in a weird scientific notation way that we're not going to explain today. Wait until CSCI 45 if you want to fully understand it. But they can store numbers as small as this to as big as this with about 16 digits of precision. So it's being stored in like scientific notation. There is, the reason it's called double, by the way, is there's a type called float, which you might have read about in your book by now, which takes up 4 bytes and also stores decimal numbers. So double is twice the size, and we'll just keep using that one because we can. Okay. There's other integer types, like these guys. There's a short. A short type is halfway between, it's like half the size of an int, 2 bytes. It can store this range of numbers in smaller amounts of space. And then there is a long, it's like a type with a space in it, which is funny. It takes up 8 bytes and it can store even bigger integer whole numbers. Okay? And so you can use all the ones you want. We're usually just going to use ints and doubles and chars in this class, but the rest of the table is important too. But I need to teach you, like, what is a byte if we don't really know what that is. Like, we've bought, like, maybe we bought flash drives before, and like we bought like 16 gigabytes or something. We bought RAM for our computer, but we don't fully understand, like, what does it mean to take up space? So I'm going to teach you now. We're not going to program for a little while. I'm going to teach you how to convert between bases in numbers. So this is kind of like a math lesson today, this first part at least, right? So, yeah, there's a lot of new terms when we're doing this. So the numbers that we know and love as humans right now, they are written, we use base 10 as humans, all right? And the reason we call it base 10 is that we have 10 digits that we use to make our numbers. We have these guys, 0, 1, 2, all the way to 9, right? That's 10 digits total. Digits total. Another word for base 10 is decimal. We use the decimal number system. It's the base 10 number system, right? I'm going to teach you about different number bases in this class, and so I'm going to have to differentiate between a number written one base rather than another, right? So whenever I mean a decimal number for these slides, I will write 100, and if I mean really the decimal number 100, I'll put subscript 10 here to mean we're talking about this number in base 10, right? Because there's other bases, and you can extrapolate from this. Like there's a base 5, and how many digits can you make with your numbers? How many digits can you use to make numbers in base 5? Well, you have only 5 of them, right? You get 0, 1, 2, 3, and 4 to build your numbers with. Ooh, odd. And so, let's see. There's also the number 100 base 5 because it's using these digits, isn't it? But these are not the same number. This isn't even 100. It's something smaller because it's a smaller base. And I'll talk about how to convert and everything, all right? Does that make enough sense so far? Different bases have different digits that you can use to build your numbers up with, all right? We like binary a whole lot as computer scientists, and binary, another word for that, is base 2. That's why we're doing this, right? Which means you only get 2 digits to work with when you're building numbers in binary. You're representing them in binary format, right? You get 0 and you get 1. That's it. So that means 0 in binary is 0. 1 in binary is, of course, 1. And then if you add 1 to 1, you want the number 2. How do you represent the number 2 in binary? Well, I've ran out of digits in this place, haven't I? So I need to add a new place. 1, 0, base 2, must be 2. My decimal 2 that I know. Does that notation make enough sense now? Slowly getting it? So do yell at me if you have questions about this, but this is the base we like a lot in computer science. And we use binary so much, we've like contracted words like bit. Bit is short for binary digit. You took the B from there and the it from there. And so, for example, we can talk about how many bits are in a number. Like this is some binary number. I'll tell you how to figure out what it is soon. But that's a 4-bit number, right? Because it's using 4 binary digits to build it. You'd think I'd be really good at drawing curly braces by now. I am not. A 4-bit number. Okay? And this leads naturally into the idea of space, right? Because if you use a certain number of bits, you have that much room to make your numbers. That leads to a concept of memory and space, right? So a byte, we say, is 8 bits. Like that's the smallest chunk of bits that we care about. So a byte is any string of 8 bits. So like 1, 0, 1, 1, 0, 0, 1, 1. That's 8, right? Base 2. That's 1 byte, right? That's 1 byte of space. Byte of space. And the smallest byte is 8 zeros. Takes up a byte to store 8 zeros. And the largest byte, that's like the biggest number you can make with 8 ones and zeros. That's 8 ones. Okay. So yeah, I need to teach you how to convert, though, back to the numbers that we understand as humans, but that's a start, right? And the theory is, the reason we use decimals is because we have 10 fingers, and so like we count in our fingers, and then we add a new place after that. And so maybe if you were living in like the Simpsons world or another cartoon where they only have 4 fingers, maybe they're using base 8. So I need to teach you how to convert now. Let's convert from binary to decimal, right? And the secret lies in a lot of things that you learned in elementary school and also middle school. So do you guys remember how you first learned how to break down big numbers like that? You learned that, all right, 1,234, that's equal to, like elementary school, you're like, that's equal to 1,000 plus 200 plus 30 plus 4, right? And once you learned a little bit more, maybe you learned about powers in middle school or something, like you get a little bit fancier after that. This is equal to 1 times 10 to the 3 for the thousands place, plus 2 times 10 squared, plus 3 times 10 to the first, plus 4. You can still multiply by 10. It's got to be 10 to the 0, yeah? And what do you know? We're working with decimal numbers. There's that base appearing secretly there. Huh. So that is the secret. That's going to generalize to binary, okay? So let's do the same. Let's convert this binary number, 10010. Let's convert that back to decimal by playing the same game. We're going to expand the powers, right? You always want to start from the right side. Like this is the not 10 to the zeros place. It's going to be the 2 to the zeros place, okay? Because that's the new base we're working with. So whatever this number is, it's equal to, well, we got a 0 times 2 to the 0. That's still the ones place. Plus, this is 1 times 2 to the ones place, right? 1 times 2 to the ones place. So that's the 2's place. Plus 0 times 2 squared. That's the 2 to the 2's place. That's the 4's place in binary. It's weird, huh? Plus 0 times 2 cubed, the 8's place. Plus 1 times 2 to the 4th, the 16's place, right? And so if you do the math, 2, 4, 8, 16, right? This is 2 to the 4 plus 2 to the first plus nothing else, right? So that's equal to 16 plus 2. So that number was representing, in binary, the decimal number 18. And that's how you figure it out. Questions about that? Not horrible, right? You got to start with the right side, though. Yes?
How do you get 0 times 2 to the 0 power?
Just like I broke it down, this was 4 times 10 to the 0. This was the rightmost digit. It was a 0. We're working with base 2, so 0 times 2 to the 0. Yeah. Anybody else? All right, so your turn. I would like you to, as a group, the people sitting next to you, you don't have to write this down anywhere, but help the people around you. Introduce yourselves, take a couple minutes to convert this number, 1111 base 2, to decimal. Here's my scratch work from this slide. I'll copy and paste it. Not there, but here. See if you can figure it out. Help your neighbors. What's the biggest 4-bit number? Figure it out. Another minute or so. See what we're thinking. All right, that's my timer. I think I messed something up. Somehow I did that. I don't know how. There. Back to the normal looking slide. Any brave souls want to share what they think the answer is? Yeah.
We think the answer is 15.
Do we agree? All right, nice. It is going to be 15. Let's break it down together. So rightmost digit, we got 1 times 2 to the, not the 1, but the 0's place. It's always the 1's place, regardless of the base. Plus 1 times 2 to the first, plus 1 times 2 squared, plus 1 times 2 to the third. All right? So that's going to be equal to 8 plus 4 plus 2 plus 1, which is 15. Nice. 15 in decimal land. Any questions about how we got that? All right. So that's how you go from a binary number to a decimal number. How do you go in reverse? Like if I gave you 15 or something, how would you produce 1111 in an easy way? What's the algorithm for that? So I need to teach that to you. This is the harder way, sadly. Question first? The 10? What did you say? 10? Oh, this is the base. This is a binary number. It's not 1111. And so I need to specify what base I'm in by putting a subscript. This means interpret this as a binary number, and this means this is a decimal number, base 10, like humans know and know how to use. Okay? All right. So yeah, let's go the other way. That's the harder way. So pay extra attention to this one. We're gonna need a new kind of operation in math. You know it already, but I just need to give a symbol to it because you haven't probably used it before, just by itself. I'm going to use the percent sign to mean take the remainder. It's going to be the remainder operation after dividing. It's also called modulus. That's like the fancy term for it. And so if I write 10% sign 2, I'm going to pronounce that as 10 modulo 2, or 10 mod 2 for short. And it means try to divide 10 by 2. It's like pretend there's a slash there. It's almost a slash. And instead of giving the 5 back as the answer, give me the remainder back as the answer. 0 is going to be the answer. Okay? So 10 mod 2, the answer is 0. So give me the remainder after dividing. I'm going to need that. Okay, and so this is going to lead to an algorithm for extracting the binary numbers of a decimal number. So an easier thing to do first, just to get us started, that we'll generalize, let's start with a decimal number and let's extract the decimal digits of a decimal number. All right, so how do we, like, if we were able to do it, if this were just like a black box, but we could do math on it, we didn't know it was 1,234, how could we like extract each of the digits from it? And the modulus is going to give us the answer. So it has to do with this. We're going to start with 1,234. And we're going to do a modulus by 10, because I'm trying to extract the decimal digits. Do you see that if I divided 1,234 by 10, and I ask for the remainder, I get 123, right, as the answer, but remainder 4. Remember doing that when you first learned division? That's what I care about. And do you see how that's going to spit out the 4? Just the 4 by itself. I got one digit out of the number. All right, so this will give back the 4. And now, if only, right, if only I had a way to convert this number to just 123, because I could do the same thing to that. Get the 3 out, get its rightmost digit. And I can. I can do 1,234. Give me this part. That's the 123. Do not modulo 10, but do integer division by 10. Yeah, chop off the decimal places. No 0.4 for us today. That gives me back 123, and now the process can repeat. I can get that rightmost digit of 123 by doing mod 123 mod 10. It's like 12.3, or 12 remainder 3. That spits out the 3. I got another digit. See that? And now let's shift away, get rid of that 3, chop it off by integer dividing by 10. That'll give me 12 back. Does that make sense? So now I got the 12, and I can get its rightmost digit, right? This is my algorithm now. This is the process that repeats. 12 mod 10, get its rightmost decimal digit. Bam, I get the 2. Chop off the 2, shift away the 2 in decimal land. 12 integer division by 10. I get just 1, right? And then, let me move all this up so I have more room. All right, and now I got the 1. Let's get the rightmost digit of 1 by doing 1 modulo 10. So 1 divided by 10 goes in 0 times with 1 left over. There's my 1. And now let's shift away, cross off the 1, see if we're done yet. 1 integer divide by 10 gives me 0 back, because it's 0.1. Chop it off. And once you hit 0, the algorithm is complete. You've extracted all the digits. Okay? And every time you took a modulus, you did a remainder operation in reverse order. In reverse order, you got your digits. There's the 1, there's the 2, there's the 3, and there's the 4. So if this were just a black box that you could do math on, you know how to get all of the digits out. Okay? That's how you can extract them all. So yeah, instead of thinking of this as like 123.4, it's 123 remainder 4. All right? So look at what I'm doing. I'm trying to extract the decimal digits of this number. What do you know? The base is appearing. Ooh. So this generalizes to any base. All right? So you just keep on repeatedly, instead of mod 10ing and integer dividing by 10ing, if I want to convert a decimal number to binary, I want to extract binary digits. I'm going to do mod 2. I'm going to do integer divide by 2. Okay? That's the secret. So repeatedly divide, take the modulus by the base you're trying to go to. So we know the answer to 15, right? 15 decimal is equal to this, 1111 in binary, base 2. But if you didn't know, we could run that algorithm. So here's what we start with. We start with 15. I would like to extract the rightmost binary digit, the rightmost bit of 15. So I'm going to do mod 2. What is the rightmost digit in binary of 15? And a quick way to do mod 2 is, if it's odd, there's 1 left over, right? It's going in 7 times, but there's always 1 left over. If it's odd, because it never goes in cleanly when dividing by 2, because it's not a multiple of 2. It's not even. And then, all right, so the rightmost digit of 15, rightmost bit in base 2 of 15 is 1, perfect. And now I want to shift away that 1 out of 15, all right? I'm going to get rid of it so I can convert a smaller number to binary and tack the 1 at the end. So I'll do 15 integer divide by 2. which is going to be 7, right? Because it's 7.5, chop off the 0.5. And so now if I could just convert 7 to binary, I put a 1 at the end of that, I got my answer. Right? That's the algorithm. 7 mod 2. That is again odd. So it goes in, 3 times with 1 left over. So there's my 1. I got the rightmost bit of 7 in binary is 1. I want to now chop off, shift away the 1, push it out of there by integer dividing 7 by 2 now. That'll give me a smaller number to then convert to binary. Right? And that's going to be 3. And now I just need to convert 3 to binary. What's its rightmost bit? 3 mod 2. That is equal to 1 again, because it's odd. And then, all right, let's chop off the 1 in binary land out of the 3. That's going to be integer divide 3 by 2. It's 1, right? 1.5 becomes 1. And then, all right, let's get the rightmost bit of 1. And that's going to be 1 mod 2 equals, well, it goes in 0 times with 1 left over. And then finally, chop off the 1 from 1 in binary. Integer divided by 2, we get 0. And that means we are finished. So again, every time we took a modulus, we got the remainder. And in reverse order, even though it's the same order this time because they're all 1s, we got the digits. So it's 1, 1, 1, 1. We know now that 15 in decimal is equal to 1, 1, 1, 1 in binary. Make enough sense? I know it is a weird operation, I know. Yeah.
Did you take off to the 0.5 then?
I've been doing integer division, yes, so I'm always chopping off decimals. Yep. Yeah. Questions? The rightmost bit, we got this rightmost bit first, and that's always going to be your base to the zeros place. Yeah. Just like when we did it this way, it was our ones place, 10 to the zeros place. Question, yeah. Here? That's because I want to chop it off. I do that division to chop it off. It's kind of like I'm doing it here, but it's in a different base. So just like I'm done with the 4 now. Now if I just had this, I can do the same thing and get the rightmost digit of 123. How do I get 123 from 134? I divide it. So same in binary. How do I get rid of that 1 that I just got out of here and give me a smaller number to then convert to binary? I'm going to integer divide by that base. It does seem a little magical once you're first learning it, but the more you do it, the more it'll make sense. So good. So yeah, let's keep on trucking. It's your turn now. All right. So here's your question. I would like you to convert 117 to. Is someone knocking on the door? The door is unlocked. They're both unlocked. I swear it's unlocked. Just pull really hard. Yeah, that's weird. That's a weird one. Okay. Your turn. So I would like you to convert 117 base 10 to base 5. Not base 2, base 5, please. So what are the digits that make up base 5 numbers? 0, 1, 2, 3, and 4. And so, as a sanity check, make sure your answer is only holding those. But here is the general idea. Your turn. Convert 117 to base 5. You might need a calculator. And let me know if you have questions. You're going to do this process all over again. And if you finish early and we're not ready to come back yet, you can check your answer, right? The easy way is going the other way, back to decimal, isn't it? You can immediately check your answer. Yep.
Could you explain it one more time?
So it's the modulus tile looks like a slash. That's kind of like division. It's 15 divide 15 by 2. And then what is the remainder? Not the answer, not the quotient. What's the remainder? So it goes in 7 times, right? But there's 1 left over. 14 plus 1. 1 left over to make 15. It's like 7 and 1/2. The 1 is the remainder. What number are you going to mod by and divide by? 5. That's the base you're going to. Give me another minute. Yeah, this is easier because now I don't have to like flip that down every day. I can just stand up. What?
Want the chair?
I'm good. So, yeah, you can have it. Exactly. You can use the good chair. Recording. Alright, that's as much time as I want to give you. What's that? No, it's just this question. Just let me work on this question. Alright. Any brave souls want to share what they think the answer was? Are you able to check it? There's a way to check it, right? Alright. On speaking of attendance, we've all done attendance, right? I can stop that now? I'll give you another minute to do that if you haven't. Alright, so, no takers, we're all afraid of our answer. Whatever. 432? Nice. Yeah, good. So 117 is our decimal number. I want to convert that to base 5. So I'm going to start by extracting the rightmost base 5 digit of 117. 117 mod 5. And this is hard to do in your head. Maybe it's not, because like the closest multiple of 5 is 115 maybe. So maybe it's easy to see that there's 2 left over. Maybe it's not. I don't know. But you can use a calculator. That is fair game for this class. Eventually, there will be a modulus in C++. That's the reason we're using %. So 2 is the rightmost digit in base 5 land of 117. Now I need to chop off that 2 in base 5 land from 117. I need to like shift it away. So I'm going to integer divide 117 by 5. And I have no clue what that answer is. 23? I trust you. Or 43? I don't have to trust you because I can just use the computer. 23. Nice. And now I just need to convert 23 to base 5. What's the rightmost base 5 digit of 23? I'll figure that out by doing 23 mod 5. Goes into to make 20, right, with 3 left over. And now let's chop off the 3. Surprisingly, it was the same as the decimal digit, which is never usually the case. And then, yeah, I need to do 23 integer divide by 5 now to chop off that 3 and give me a smaller number to then convert to base 5. So it goes in 4 times, right? 4 times with that 3 left over. Alright, and now let's extract the rightmost base 5 digit of the number 4. 4 mod 5 goes in 0 times with 4 left over. And now let's chop off the 4 just in case there's any more. 4 integer divided by 5 is 0. Alright, so that's when the algorithm has completed itself. And we know we're done. And we got digits of this number, and we got them in reverse order. It's always the rightmost, then the next rightmost, the next rightmost. So it's really 4, 3, 2 is the answer. Right? 4, 3, 2, base 5 is our final answer. Any questions about that? And we know how to convert it, right? Yeah. That's just the modulus. It goes in 23 times. The answer is 170 divided by 5 is 23 and 2/5, and the 2 is the remainder. That's all I can really say, I think. And if you are not convinced that you got the right answer, you can always check your answer on a test, right? You can go the other way. That's the easy way. What is this? Convert it back. 2 times 5 to the 0 plus 3 times 5 to the first plus 4 times 5 squared. Yeah. That's equal to what? 25 times 4 is 100 plus 15 plus 2, which, yes, is 117 base 10. Checks out. Okay? So you can always check your answer. Is it good? We learned a lot of weird stuff that we've maybe never seen before. All right, now we can go back to programming. Now you know more things. And now you can understand this table a whole lot more. Integers, they are 4 bytes long. Every integer is 4 bytes long, and another word for that is 32 bits, because every byte takes up 8. Every byte takes up 8 bits. If there's 4 of them, we got 32 total. And you can kind of understand why we're getting this range of numbers now, because I haven't told you how we store negative numbers, but you can imagine the smallest int is 32 zeros, more or less. Disregarding negative numbers for a second. 32 zeros, and the largest int is 32 ones. And this is what, the 2 to the 31st place or something, and that's kind of why we get that range, yeah? That makes a little more sense now. And that's also why chars, 1 byte, has such a small range. There's only 256 possible values, 2 to the 8. Yeah? That's the secret. Doubles are a little weird. You'll have to wait until a future CSCI class to understand what's going on there. But yeah, that's how everything works. So the number 1, first of all, the number 1 as an int, it's always being stored as 32 bits, as 4 bytes. So the number 1 as an int inside of your computer in terms of binary, as zeros and ones, is a bunch of zeros, ... padded with zeros, and then a 1. There are 31 zeros and then the 1 at the end. That is the number 1 as an int inside of your computer. Okay, in binary. So I hope that makes at least a little bit of sense. Now we can go back to programming. So I would like to teach you about a magical thing called a const qualifier that you can put in front of variables. You can put the word const before any type as you're declaring a variable, and that makes sure that that variable is a constant value. It makes it like it's really a mathematical variable with the equal sign and everything. It can never be changed after you set it, all right? So you have to initialize it on the same line, otherwise it makes no sense because you can't change it after that. So this is something you would probably want to do. Const, instead of just double pi equals 3.14, because you could change pi later accidentally, you can say const double pi, and the compiler will make sure you never mess with it, which is good because we mess up a lot as programmers. All right, so let's do that. Const.cpp. Oops. Boop. So yeah, I can say instead of double pi equals 3.14, I can say const double pi. All right, just put it out in front of the variable as I'm making it, and now pi is a constant variable. You can't change it, which is exactly what we want for pi, right? You can't come along and say, oh, you know, pi is 3 now, because you would if it wasn't a const, right? You totally could do that. But now the compiler makes sure that that can't happen. If I try to compile this, boop. Assignment of read-only variable pi. It's a read-only variable at that point. All right, that's what it's called. So that's really nice. It won't even compile. So it can't do silly stuff like this now. All right, so if I want this to compile, I have to get rid of that. So that's constants. Not too bad, right? Use them as much as humanly possible. If you have a variable that shouldn't need to change, make it a const, because then you can't accidentally change it. All right. Oops. There. Next, let's finally talk about functions. We're ready for that. All right. So I've said that word a whole lot. Main is a function. We're calling a function. So, okay, here is what a function call looks like. It's a weird metaphor. So, first of all, a function is just some code that somebody wrote, right? So you're writing a main function. That's code that you wrote. A function is a piece of code that somebody else wrote, maybe you, that you can what's called call it multiple times. Like the metaphor is like you're shouting to this function, hey, please do this thing for me, and it shouts the answer back, all right? And so, gosh, what's the best way to explain this? Yeah, there's more to it. So like, as you're calling this function, asking it to do something for you, again, the metaphor is you're shouting at it. So it can take 0 or more things called arguments, all right, which go between the parentheses, comma separated. And those like give information to the function to tell it like what exactly you want done. Do exactly these things for me, please. Controls the function and the way it executes. So a lot of the time functions give back an answer, and then like you pretend that your call to the function gets replaced with that answer. So let me give you some examples because that probably makes no sense at all. All right. So there's a cute little function in a library called rand, which takes no arguments. So you just say rand, and then you give 2 parentheses, just one after the other, and every time you call rand, it produces a random number between 0 and some giant value. All right, so maybe this time we call that gives back this number. I don't know. Rand is a function that you can call, and it gives you back a random number. That's pretty nice. That gives you the ability to make video games, for example, and have it be a different game each time. There's another function in a math library called pow, which is short for power. It computes like 2 to the 3.5 power. You can't really write that in code very easily. And so you use the pow function. You call the pow function. You say, all right. And pow, by the way, takes 2 arguments, the thing that you're trying to take to a power and then the power itself. So you call pow like this. You say, take 2 to the 3.5 power, please. And like this will give you back that answer. And like you can use it in a larger context. You just pretend it's getting replaced with that answer. You like add 2 to that or something. Just pretend it gets replaced. That's pretty nice. And yeah, the last one is called square root. People wanted to shorten it, so they called it that. And so you can ask for the square root of a number. Square root, SQRT. What's the square root of 2? It's like 1.41 something, right? And you'll be given that back to you. Somebody made this nice square root program function for you that you can call and ask for the square root. And as you would expect, it takes 1 argument, the thing you want the square root of. Okay. And so, yeah, you can do math with it. You can like feed it into cout. Like, hey, please give me this thing. Give me this result. And so that's functions in a nutshell. Any questions so far? So this is how it works. You say its name, and then you put parentheses, and if there are arguments, you comma separate them in between the parentheses. All right? And the arguments control how the function works. Like power needs those 2 things. You can't just give it 1, give it 0. You need to know the thing and the thing you're taking to the power, right? The thing and the power itself. All right. Yes.
The random function.
Yep.
What do you put inside the parentheses?
Nothing. You say nothing at all. It takes no arguments. Because you don't need to control it. It just needs to know that you're running it. Because it's like, all right, I'm rand. I'll give you back a number each time. It'll keep giving you a random number each time you call it. Yeah. Other question. You sure can, and we'll get into that later. Yeah, I'm going there, I promise. So yeah, let's start with learn a little bit about the math functions, and these live in these libraries. We got the cstdlib and the cmath libraries. They're from the C language, and you can look up functions. There's a documentation page. There's a cute little website called c++.com. But honestly, you can just do this. You can do just Google it. I'm going to stop attendance now after I go to this page. You can just search for C++ and then the name of the library you want to know about, like cstdlib. And then the first link will be to that website anyway. And so then you can scroll down and see, oh, these are all the different functions that live within this library that I can call and use. There's rand, for example. All right, so it's a very useful page. I lived on this as a student. You will live here too. What do I want to do first? Let's talk about mathy stuff first. And so in addition to cstdlib, which is where rand lives, there's also the cmath library. And you can get here on the left as well. There's CMath right there. And like, there's a bunch of functions that do exactly what you expect, like sine, cosine, tangent. Obviously, that would be in the math library. Computes those answers. And then there's more. So I think the first one I want to show you is this exp function. And if you want to know more about any function, you click on it. And it tells you like what it does. And if you scroll down, it even gives you an example. Blah, blah, blah. It's being called right here, and it's being used. So yeah, the way you read this, first of all, I'm going to teach you how to read this. It's a little small right now. This will make more sense later. But this exp function gives you back e to the power of something. So it takes one argument, so like exp of some value, and it gives you back e to the power of that value. So if you just want the number e, that constant, you can just ask for exp of 1, because that'll compute e to the first power, which is e itself, right? And this is how you read these functions and know what it takes. So exp, that's how you read this. Exp is a function that takes one double argument, and it gives you back a double. It's kind of all over the place. This is what it takes. This is what it gives you back. All right? Memorize that. Commit that to memory. That's going to be very important later. All right? Just like main gives back an int. That's why you say int main. So, we'll go further with that later. But let's include the CMath library and compute e by calling the exp function. And then also, like we've got also in this library, we've got what? We've got square root. We've got pal. They live down here. All those fun guys. So let's do some of those too. And again, they work as you would expect. Square root, what does it do? It takes a double, gives you back a double, which is the square root of the thing you were asking for, right? Scroll down for a mini example if you need it, but let's code that up. So math stuff.cpp. So I need to include the CMath library if I want those things. And now I can just start using them. I'm like, all right, I would like the square root of 2.0, please. And you can just imagine that the function call, you'll call it, it yells the answer back, and this whole thing, this whole place that I was talking here, this whole text right here is going to get replaced with the answer. And so just pretend you have the answer, use it, like see it out or something, or multiply it by 42, whatever you want to do. You can use it in a larger context if it gives you back an answer. So there's that, and like, all right, exp of 1 or 1.0, doesn't matter, it'll be converted to a double. So yeah, that's how you call functions. It's code that somebody else wrote. So there's the square root of 2, and there is e, which is e to the first power. Same, right? We're good so far. It's just somebody else's code. It's not too bad. Let's see. I've got a couple functions I want to teach you. Yes. Sorry. That's exactly right, because this is where these functions live. In the CMath library, I have this list of things that I get by including it, and that's where square root lives. Then the compiler would complain. It's like, I don't know what you're talking about. I don't know what square root is, because it hasn't been defined. It's the library that tells you where it is and what it is. It defines it. Yeah. Good question. So you always got to include your libraries. Sometimes they're included for you secretly, like string. I forgot string once, and it worked somehow, but it usually won't compile. All right, so there's those guys. I want to next teach you some rounding functions. So we've got two things that are very mathy. You've got normal rounding, and then you also have these guys, ceil and floor. Ceil is short for ceiling. So here's the metaphor. These are two rounding functions. So like ceil performs the ceiling operation on a number. It takes a double, it gives you back a double rounded upwards, shoving it up to the ceiling. So here's the idea. It's like if you have 2.15, you can feed that into the ceiling function, and it will always round it up, like push it up to the ceiling, wherever it is. So 2.15 will get rounded up to 3. All right? That's what ceiling does for you. And then floor, another fun metaphor, it's like shoving it down to the floor. So even if you had 2.99, it'll still give you back 2. 2.15 shoved down, you get 2 back. All right? So there's those. Let me show you those working, and then I'll show you like the normal mathematical rounding functions. So see how it's ceil of like 2.15. That'll give me 3. Floor of 2.15 will give me 2. Floor of even 2.999, whatever you have here, still shoving it down into the floor. All right. So there's my 322. All right. So those are some rounding functions. And then there's also a normal rounding function. There is, promised that I would stop that. There's just one called round, and that's the one you'll use the most probably. Round takes a double, gives you back a double. It's the rounded to the nearest number that you learned about in math, right? 2.5 and above makes 3. So round is the normal mathematical rounding. Round on 2.15 will give you back 2 because it rounds down, smaller than 2.5. And then round on 2.5 and above will make 3 happen. Okay, so that's the normal rounding that we know. Let me show that to prove it. Dun, dun, dun. So let's take this and do round on that, and then I'll also round 2.5. So these are function calls. We're asking somebody else's code to do stuff for us. We're so thankful to the library implementers because we don't have to do this ourselves anymore. Just get to use their codes. There's the 2 and there's the 3. Round it down and round it up.
So when you use like the round function, is this going to round like properly, like normally?
Yeah, just like math, just like I said. Yeah. All right. Are we ready for random numbers? That deserves its own slide. So, okay, here's rand. Rand is a function that lives in cstudlib, which is short for C Standard Library. There's rand. You click it. It gives you information. It takes nothing. It takes the emptiness. It takes the void. Gives you back an int. And it gives you back a number between 0 and some constant called rand underscore max, all caps. So here that is. It's just some big number. Implementation specific, so we're not actually sure what it is unless we try it ourselves and print it out. But that's what rand does for us. So yeah, every time we call rand, it will produce a random number for us. All right. Dun, dun, dun. So let me show that to you. Rand.cpp. So if I want to use rand, I need to include cstudlib, and then every time I call rand, see out rand, it'll give me a number between 0 and some constant in the library called rand underscore max, which I can print out. What is the largest possible value I get that's a random number? Rand underscore max. Oh, sorry, not math stuff. Rand. Or even for fun, let's print out a few random numbers. 3. Rand. So yeah, apparently rand max is that number. That's actually the largest positive int, so that's as good as it could get. And then here are our 3 random numbers. Cool. They're very large. They'll usually be very large, right? And then if I rerun the program, it should give me more random numbers. Question first? Let's see. A good example is, like, let's say you're making, like, what's the simplest game I can think of right now? Let's say that, like, you're making, like, a Sudoku game or something, and you want to make a fresh board to play with. You can just put all the numbers in order. You can just produce a random number each time, maybe, with respect to some rules. That would work. Or you make a video game and, like, you want enemies randomly placed on the screen, and so whenever you rerun the program, like, sometimes they're over here, sometimes they're up here, so it's, like, different every time. Yeah. So that's kind of the idea. Was there another question? All right, so yeah, if I run it again, I should get new random numbers. Technically possible, unlikely, technically possible for me to get the same random numbers. Let's run it a third time just to be sure. I'm getting the same random numbers every time I run this program. That's not so random, is it? So there's an issue here. So rand doesn't give you back a truly random number in the sense that, like, if you have like a photon detector at some radioactive particles or something, like, that's true randomness. your computer it can produce true randomness, but you can't get that with a rand function. Rand is called a pseudo-random number generator. All right? If you go to the thing, it actually does say that. Pseudo-random integral number. It's good enough for most purposes. Right? That's why we have it. But it's a little special. What it's doing is, in a very weird way, it's computing a sequence of numbers. And it's always starting somewhere. So like the first number in the sequence is like 1, and it uses that to produce the first random number that you call. And then it's like it uses that to produce this giant number. And then we're off to the next. Then it produces the next number in its little sequence based on the previous one. And then it uses that the next time you call rand to produce some other number. Like the sequence has this number, and then it uses that to produce the next number, and so on and so forth. It's just like there is a process. There's an algorithm to compute the next random number, and it ends up being randomish anyway. So it works out. But our issue is that by default, that sequence that generates our random numbers every time we call rand starts with the same value. So what we need to do in order to have a different random number called each time is we need to start off the sequence in a different spot every time you run the program. All right? So we have to what's called seed the random number generator. It's like we're pouring water on the random number garden. And that will give us a different sequence of random numbers each time, and then it will appear truly random to us as humans. Right? So that's where the srand function comes into play. This one goes hand in hand. That initializes the random number generator to some number, right? So it takes an int, and that seeds the random number generator, right? It actually gives back nothing. You just call it on a line by itself. So, yeah. What you want to do is every time you run the program, you want to seed it with a different number, because that starts off the sequence in a different place, and it'll give you a different random number after that each time. So what's a good number that's different every time you run the program? If you scratch your head for long enough, you will realize that the current time is always a number that changes between runs of your program, right? If we can convert the time to a number, and we have, there's a function called time that does that. If you give 0 to the time function in the ctime library, that will give you the number of seconds that have passed since January 1st, 1970 at midnight, for a weird reason. And so that's a number that increases every time I run this program. If I seed the random number generator with that, then I will get a different random number each time. Does that kind of make a little bit of sense? That's going to be the secret. We're always going to do this first before we do any rand calls, because then the sequence is started somewhere different. All right? That's what we do here. So srand is part of cstdlib, and then the time function is part of ctime. So you give it the number 0, and it gives you back the amount of seconds that somehow represents the current time. Right? So ctime. And so what I'll do now is I'll seed the random number generator. I'll do srand. And then I'll give it a number, a secret number. I guess you can ask the user, enter a random number, please. Srand times 0. So again, this has to do with, you get to imagine that function calls get replaced with their answers. Like times 0 is the first thing that happens. It produces the current time as a number. That gets like replaced now with whatever the current time is as a number. And then you're calling srand with that. That's how this works. That's how you can chain function calls. Seed the random number generator with the current time. Okay. And then now the sequence is off and different. If I rerun this program and I wait a second in between calls, runs of the program, now I get different random numbers every time. And now I can make a game that actually is different and exciting. Okay. Are there any questions about this so far? Yes. The minimum is 0 right now. So every time you call rand, it's guaranteed to give you back a number between 0. It's always 0 and rand max. Yeah. But you can change it. I'm about to teach you that. So let us have a demo. So let's get a random number between 1, not 0, 1, and the choice of the user. So if the user asks me for, like, they give me 100, I want to generate a random number between 1 and 100. If they give me 10, I want to generate a random number between 1 and 10. So whatever the user gives me, call it n. How do I generate a random number between 1 and n is my question. All right. So we're going to have to call rand, right? To get a random number between 1 and some number, call it n. Maybe it's 10, maybe it's 100. What can I do to rand, potentially involving n? to end up with a random number between 1 and that number n. Does anybody see it? It's going to involve an operation that we learned about today already. You have an idea? You have a question? What's that again? Okay, good. That's a good start. How can I do that first thing, though? How do I get a number between 0? What's that? Well, the random is always going to give me a number that is interpreted as decimal. But it's too big. It's going to be between 0 and rand max. It's giant right now, usually. It's going to be way bigger than I want it to be. How can I shrink it down? Yeah. Can't change rand max as a constant. Can't change constants. So if you think about it long enough, how did I make big numbers small? I used this guy. Every time I did mod 10, I got a number between 0 and 9, didn't I? That made a big number small. That's it. That's the secret. If I use modulus in the right way, I will be happy. All right. So rand, if I give rand an n to mod, giant number over here, whatever n was over here, do you see how that will give me a number that is random between, starts at 0 because that's it could have gone in evenly, 0, 1, 2, all the way to n minus 1. Okay? All the way to n minus 1, because if it went in n times, it would have been wrapped around back to 0, right? Because there's nothing left over. So that's the possible remainders when dividing by n. Yeah. But I want a random number between 1 and n. Do you see how whatever I got, that was the first student's answer. If I just add 1 to whatever I get after that, now if it was a 0, now it's a 1. If it was n minus 1, now it's n. Everything in between got shifted over as well. Whatever the random number was, now it's between 1 and n. That's going to be our secret. All right, let's watch that work. Think about that as I'm coding it. That's going to be our answer. So first I'm asking the user, should work for whatever they give me, as long as it's a positive number. Enter a number, please. Make room for it, get it with CN. And then my goal is to calculate a random number between 1 and n. So what I will do, I will see out, not just rand at any line, I will see out rand mod that n, whatever the user gave me, 110. That will give me, let's say it was 100. Then I got a number now between 0, it's random, between 0 and 99. But I want it to be between 1 and 100, so I'll add 1, shift it. And now it is between the proper values. Technically, I don't need the parentheses, but I'm going to add it anyway, just because it's going to make your life easier as you read this later. All right, enter a number, 100. Oh, my random number was 1. Enter another 100. Now it's 86. It's always being shrunken down, right? Always being shrunk down. Isn't that cool? Isn't that so cool? And all right, give me a random binary number. 2. Between 1 and 2, now I get 1, sometimes 2, sometimes 1. Random number between 1 and 10. 10. Different every time. 3. 9. Cool. So that's the secret. That is what you memorize, and that leads to very interesting programs. Okay? Yeah? That was the number that I want to calculate a random number between, that range, between 1 and whatever I typed. That's what I'm asking. I never did n minus 1. There's no n minus 1 in this code. Yeah, that's what the modulus gives you back. If you take a number and you do mod 10, you should try this actually. If it's weird to you, just think of write down a bunch of random numbers and do mod 10 on them, and you'll notice that you'll always get an answer between 0 and 9. That's what remainders do. Other question? Because I want that number from the user. Because I want, as the program runs, I want the user to give me a different number potentially every time the program runs. Sometimes I want a number between 1 and 10, the user types 10, or sometimes I want it between 1 and 100, or like 1,000. I get to type that and control it as the user now. Yeah, CN stops the program, and it waits for the user to type something, and it feeds it into a variable. Yep. Good. Yeah, you'll definitely learn more about that as I force you to read your textbook if you haven't already. All right. Just for fun, characters are numbers, right? So let's compute 3 random characters. Why not? What's the biggest character value? Let's not deal with negatives. So let's go up to 127. Character value between 0 and 127. So I will modulus my rand call by, to get a number between 0 and 127, I will mod by 127. 128. Think about it. All right. So char C1 equals rand mod 128. Same with C2, C3. And I'm just going to print them out. We'll see what they are. See out C1, no spaces. C1, then C2, then C3. 3 random numbers that get interpreted as characters. I gotta type something here. So apparently, and this is very rare, I got 3 actually printable characters. I got .w quote. That is not guaranteed to happen. Sometimes they're unprintable characters. Like here, I got a dash and then maybe 2 unprintable characters. Or no, I got the, yeah, I did. 42. Again, capital H, capital B, 3. Characters are numbers. Isn't that fun? Yes?
Why do you get like unprintable characters like
I think you'll have to go back to the other lecture because we talked about the ASCII table. We talked about all the characters that you could possibly have, and some of them are like new lines. Some of them are space. They don't show up when you print them out. Yeah. There's more than just printable characters. Yeah. All right. Couple more things. So let's talk about strings again now. Let's have some string operations, because now we understand functions and calling them, and like I told you how to get a place in a string with a .at, remember that? That's like a function call almost. It's something slightly different, but close enough. But yeah, let's talk about strings and how to do stuff on strings. I think that is what I want to do right now, yeah? Okay. So, let's say you make a string. String S equals like hello or something. What does that look like in memory? You've got S itself, and you got a bunch of indices for the little pieces, each character in the string. There's 5 characters. H, E, L, L, O at indices 0, 1, 2, 3, and 4. Yeah, so you know how to go inside the string and get something. Let me show you how to figure out like what you can do to a string. So it's on this page again. I think it's in other is where the string library lives. So there's string. And then you click on the string type, and then here's everything you can do to a string. The one thing you kind of know, the only thing you know how to do right now is the .at. So there's the at, boop, and this is hard to read. It takes an index, gives you back a character at that index essentially, and you can see it being used down here. But that's kind of how you read the documentation. I encourage you to look up. These are all the things you can do to a string. Okay. Is there a hand up over there now? All right. This, you'll notice, it doesn't look the same as these function calls. There's like name of the string, it's always s dot if that's the name of your string. Or if your string was called stir, it's stir dot at, s dot at. It's a little bit different. These ideas, they're called not functions, they're called methods. All right, we'll get into this later. It's really a method call that you're doing on a string rather than a function call. Because it's like you include the thing you're acting on. Like I'll show you the size, the dot size function. It's really called a method, right? And the reason it's a little different is because it's acting on. It's like you're giving s as a secret parameter almost. Just like act on this particular string s, please. Give me that string size. Don't give me s2's size. Just s's size, please. It acts on s, at least in these examples, right? So yeah, you know about .at. Dot size is definitely the easiest one for me to tell you. It gives you back the size of the string. Where is that? length of the string, takes nothing, gives you back a type that is a whole number that can never be negative. Think of it as an int for now. So s.size just gives you back how many characters. How many characters are in the string? If it's hello, there's 5 characters, so it'll give you back 5, right? Let me show that to you. Strings. I need the string library. String s equals hello. And then, all right, see out s.size. This is a method call. You can think of it as a function right now, that's fine. But the dot is different. So g++. Alright, so there's more that you can do to strings, of course. That's why we have this slide. So you can use the plus operator on strings, just like you can use plus on numbers. And for strings, what it does is it combines 2 strings. Combines strings. Alright, so that exists. So if you have a second string sitting around somewhere, you'd be like, oops. You could be like, if you want to make it hello world or something, s2 can be comma space world, exclamation point. And then you can make a big string. String combo equals s plus s2. And so addition on strings is just put the characters right next to each other. So now I've made the string in combo hello world. Okay? So if I see out that, you'll see what I've built up. Well, that didn't save. There we go. Yay. And so just like added the characters together and made a bigger string. Okay? So that's pretty cool. There's also find. There's a find operation on strings. You can click on it and learn more about it if you would like. I encourage you to, but it's down here. What it does is you give it one argument this time. You give it the character that you want to find inside the string. So like s.find the h character, the e character, whatever you want. And it gives you back the index where that character happens. If it finds it, it's going to go and search for it. Right? Where's the first h character? It'll go and look for it, and it'll give you back the index of where it finds it. All right? So if I ask, if I ask s for where the h is, so int index of h, and I ask s about it, or combo, s.find the h character, please. This will give me back 0. Because that is the index where there is an h. Okay? S.find h will give me back 0. I'll show that to you in a second. Let's look for an L. I can ask s, hey, go look for the L character. It will give me back where it finds the first L. So it should give me back 2, 0, 1, 2. You can also ask for what is the index of like a character that's not in the string. Let's go and ask it to look for a z. Let's see what it does. Because it's got to give it back an int somehow. What's the index of h? And I'll space separate this with index of L and the index of z. And then a new line. So yeah, the h was at 0, the first L was at index 2, and then the z was nowhere, and it tells you it didn't find it by giving back -1, because -1 is an index that cannot exist. That's pretty easy. Easy to see, right? That's perfect. So that's find. There's also 2 more that I want to show you that might be helpful one day. There's s.replace. Replace is a little weird. This one is just meant to be called on a line by itself with a semicolon. It doesn't give anything back. It messes with the string though. What this does is it's going to, you give it 3 things. Right? So s.replace, starting at a starting index, that's your first argument. Replace starting from here, this many characters, len many characters, length, many characters, and those characters, I want you to replace them with the contents of this string that I give here in this third argument, s2. All right? So replace len characters from s, starting at index start, and put s2 in its place. Right? You don't have to replace it with the same number of characters either. S2 can be bigger or smaller than what you're chopping off. Right? But let me, an example is worth 1,000 words. So let's translate. All right, we've got s holds hello right now. Let's convert it to Spanish or something. Let's convert hello to hola. Okay, and how do we do that? So I've got the h already, but if I have hello right here, I want to chop off the LO part and change that to OLA, right? So using replace, I would like to s.replace. The first character I want to replace is at index 1. So starting at index 1, that's the first character I want to start chopping off from. I want to replace the LO with OLA, okay? So starting here, replace 4 characters. Chop off 4 characters, please. And replace those 4 characters with the string OLA. All right? And then now if I output S again, S will have changed. So yeah, this is just something you get practice with the more you do it, but there it is. There it's printed out. I'm still following it slowly but surely. It's good to practice it. Definitely try this later. Yeah, the last one I want to show you, slightly less complicated. This one's called substr, short for substring, make a smaller string. So what this does, this gives back something. This starts with S, and it creates a smaller string. It extracts a smaller string out of the bigger string. So s.substr, starting from the start index, take len characters and give me back whatever string was there. All right, so you can take a piece out of your string. All right, so take that many characters from S starting at index start. It doesn't mess with S itself, doesn't chop anything off of S. It gives you back a brand new string. All right, so so we have S now. S holds OLA, right? So it looks like this. This is what's in S right now, that string. Let's extract just the law part of OLA, okay? How do we do that? So string, the law part is s.substr, and I give the 2 things. I give starting index, where I want to start taking characters, and then len, how many characters I want to take starting from there. So I want the L first, so 0, 1, 2. Index 2 is where the law starts, and it's 2 characters long that I want to take starting at index 2, right? So that will give me the string I want, and I can print that out. And it does not change S itself, so I can go back and I can print S again, it's still OLA, okay? Replace, though, messes with the string. So there I get my answers at the end there. I think that is good to go. Questions about any of those examples? It's just stuff that you'll see, you'll learn more about as you read it and as you do it.
Other questions? So why did you go from 2 to 2?
Oh, okay, so I would like, S looks like this right now, it's OLA. I would like just the law out of that. And so starting at index 0, 1, 2, because that's where the law begins, that's the first 2, I would like to take 2 characters. Okay, that'll get the A with it. Yeah. All right, so I think that's all that I wanted to say and write in code today. The last thing I want to do is give you one more question. So get into groups one last time, and I would like you to think about types now that you know a bit more about them. I'd like you to please go to that written nice page that works now in theory. Clear it out. And you guys can like write as a group if you'd like. You can choose somebody to be the person who writes stuff down. But here is what I want you to do. Tell me what the difference is between if I type 1, 2, 3 in my code and if I type quotes, double quotes, 1, 2, 3 in my code. What is the difference between those two things? Try to write down as many different things as you can think. And my hint to you is think about what you could do to each of those. You can do different things, can't you? There are 2 different ideas. So tell me what you think. We'll see what you're thinking, and then we'll explain it, and that'll be that. Questions? Yeah.
You just found like different ideas.
As many differences as you can think of between those 2 things. All right, a couple more seconds. Press submit, please. Let us see. Let's come back together. I'll give you plenty of time to talk with each other after this, and then we'll see what we're thinking. All right, go into the page, viewing all the posts. Nice. I think, most of us figured out that there's a type issue here. Come back together, you guys. I'll give you plenty of time to talk after this. I can wait. All right, thank you. So let's talk about types. Yeah, so we've got, within the quotes, you have a string, right? That's the first thing we should notice. Without the quotes as an int, great. What else? What else can we say? What can you do? Good. We have concrete types, int or double even. You can do math with it. Very good. Like plus makes sense on 1, 2, 3, but not quotes 1, 2, 3. Or plus does make sense, but it's a different plus, isn't it? So that's a little odd. Yeah, very good. Very good. We got the idea, it seems. So ints versus strings, and then what can you do to each? So very nice. I'm glad that we got that working. Got those ideas right. So here's kind of how I might break it down. Here's that one. Here's this one. This one is a number. Int, double, whatever. Depends. What can you do to numbers? You can add them, subtract them, multiply them, divide them, modulus, feed them into the pal function, feed them into the square root function, all those fun things, right? Can't do any of that with this one, can you? This is a string. It looks the same when you print it, but it's completely different the way you use it. You can add them, you can add characters, or you can add two strings, but it does not do any mathematical kind of addition, like this plus this gives you back the string 1, 2, 3, 4, 5, 6, doesn't it? It's kind of useless most of the time. But you can also do other string things. You can very quickly figure out how many digits are in this string by doing dot size, if it's a string of digits, if it's just a number. You can get out a piece of it with a dot subster. Like there's reasons to do this. You just have to think hard about which one you need. You can get at each individual character of a string with dot at. Can't really do that with a number. You can extract the digits of a number, but you have to go from the rightmost one first, right? And work your way inwards like we were talking about. So it really depends on the use case, which one you need, but most often you're going to want the actual number in this class, okay? It's almost certainly a mistake in CSCI 40 to put a number in as a string and pass it around places and try to do math with it. Okay. So I think that was the moral of that story, and I think that's all that I wanted to say. Are there any questions about anything before I let you be free to work on your lab? All right, because yeah, that's pretty much it. I'm going to give you your next lab next time, so the rest of today is for you to work on stuff that's already out. All right, so yeah, that's all I got.